Okay, dear friends, the second part of the control design experiment is using simulation tool. You're going to model a mass spring damper system and then simulate the same system using the simulation tool that is available in LabVIEW, using which you can learn the dynamics of the mass spring damper system. So this is a mass spring damper system. So we'll just take the mathematical equation of the mass spring damp system. This is a mass spring damper system. You have a mass, so it is attached to a dashpot and a spring is there. Fine. So the force that is applied is given as u of t. The resulting acceleration is given as, the resulting displacement is given as y of t. The variable y of t indicates the displacement and u of t is the force. So you might remember writing the differential equation for this system. So it is m into d square y by dt square plus b into dy by dt plus k y of t is equal to u of t. So suppose I want to make it as a state equation. So m y double dot plus b y dot plus k y is equal to u. I want y double dot, so I take these two terms to the other side, which becomes m y double dot is equal to u minus by dot minus ky. So which gives us the expression y double dot is equal to 1 by m of u plus u minus ky minus by dot. Okay, this is the system we have seen. Now our thing is that we want to simulate this particular system using LabVIEW. So this equation is given here. This equation is given here. This is the input force. See here, u is the input force. Then you have three terms here, minus ky minus by dot u. All these three terms are algebraically added. So plus u minus by dot minus ky. So I use a summer. So your input force is added, other two terms are subtracted. Then the resultant of this summation, is m into y double dot. So I divide that by m. So my resulting parameter is called as y double dot. This y double dot, if I integrate it once, I will have y dot. I integrate twice, I will have y. So y dot has to be multiplied by b and it has to be subtracted. Similarly, y has to be multiplied by k and it has to be subtracted. Subtraction will give you y double dot into m. Okay. So this is your y, that is my displacement I am plotting. Okay. So this system has to be simulated using LabVIEW. So we'll see how to do this particular type of simulation in LabVIEW. So open your LabVIEW, have a separate block diagram. So here we will go to the control and simulation toolbox. There we will select simulation. So you have different utilities under simulation. All these utilities will work only under this control and simulation loop. So first you have to use this control and simulation loop. This is similar to that of your Simulink, or suppose in your LabVIEW itself, it's something like your for loop. So click on it, click, drag, so you'll get your control and simulation loop. This is my control and simulation loop. So here we can use the different parameters. So for example, step input. So I'll use a step input. That's the input force we are going to give. Then we require a summer. So summer, we require three inputs actually. So double click on that. We can make it as a square or a rectangle. So number of inputs is 4. So plus minus minus. So plus minus minus. So one input is your force. So instead of this force, we will go to the front panel. For force we will give a knob. So this is your force. So this is a force. So force is our input. Now this output is y double dot. This we have to divide it. So I use this part. So double click this, I want it as divide. So this output is my y double dot. This I'll divide it by mass. So I'll use another knob. So in Mac the controls actually changes. So we'll use another knob. This is for mass. Then we'll also use one for the spring constant, one for the dashpot. So this is spring, this is, we'll put B, this will put it as M, this will keep it as K. So these are the parameters. Force I'll just replace it by slider. The force, giving us a force. Force. Now this is divided by M. So the resultant output is y dot. This is y double dot. This we have to integrate it. So you have integrator. We may require two integrators. So this output is given to a integrator, and again that output of the integrator has to be multiplied. I'm just put reverse terminals. It has to be multiplied. This output, integrator output, has to be multiplied with B. This output has to be subtracted from my block. Then again I'm integrating. This output has to be multiplied. I'll use divide, and I will replace reverse terminals. Sorry, may not require divide, we'll use multiply itself. So this output, so here we have K. So this result we are subtracting. So this output, we want to see the output. So we'll use a graph utility. We want to see the displacement. So giving input force, this is how you use the equation, and we have to give some initial parameters. We can expand it here. So this is the initial time, this is the final time. By default it is 10. So it uses Runge-Kutta method for solving the differential equation. So all these parameters are there. So maybe the final time we can create a constant. So this is my system. So I'll give a unit step input. One. I'll set mass to some value B, K. You can also have, so now we'll just run this simulation. This is the response of the system. So system response will increase the M or will increase the B. See the response. So the dynamics of the system can be studied. What actually happens in the system is, by varying these parameters, you can see how the system drives into instability. So the first model that we saw was transfer function model. That's called as lumped parameter model. So wherein in a lumped parameter model, you can just only change the input and see what is the response, how the system behaves. You can change the values of M, B, K. Here, individually you can see the dynamics at each stage. At each stage of the input, you can see what is the output of how the velocity changes, how the acceleration changes. This is called as a distributed parameter model. That's called as a lumped model, where you have a transfer function for our direct working. This is called as distributed parameter model, where you can vary each and every effect M, B, K, and we can see what is the effect of each and everything, how the poles changes, how it affects the system. All those dynamics can be easily studied. So typical your front panel may look like this. So mass, spring constant B, I am checking the output. I am plotting the input as well as the output. I am plotting the input. This is a force that is given. Just for checking, you can use this values of M20, B4 Newton per meter per second, K is equal to 2 Newton per meter, and you can check the response of the system. And you can also have a simulation time. You can note down what is the simulation time it takes. Similarly, use alt simulation, stop button. Use alt simulation and you can get the response of the system. So these are the two ways of getting. So this is same for the same system. We are given the transfer function model also. So this is a state space equation for the same model. So using simulator to learn the behavior. So we have seen both lumped parameter model as well as a distributed parameter model. So these are additional references. Thank you.